Hello, welcome to the NPTEL online certification course on deep learning. So, since our previous class, we have started discussion on autoencoders. So, what we discussed yesterday or in our previous class is what is an autoencoder, and a particular variant of autoencoder that we have introduced is what is known as undercomplete autoencoder. Today, in this lecture, we will discuss about the autoencoder versus principal component analysis. That is, whether principal components and the autoencoder outputs they are related, if they are related, how they are related, what is the similarity and what is the dissimilarity between these two. And then in subsequent lectures, we will discuss about other autoencoder topics like training of autoencoders, sparse autoencoder, denoising autoencoder, contractive autoencoder, convolution autoencoder and all that. So, before we start today's topic on autoencoder versus PCA, let us just briefly recapitulate what we have discussed in our previous class. So, we have said that autoencoder is an unsupervised learning technique. So, a learning technique which forces the feed forward or deep neural networks to learn what is known as representation learning. That is, given an input vector or an input signal, the network or autoencoder learns a compressed domain representation or learns a structure which is present in the input data. And the way the neural network or the autoencoder learns this representation, data representation or data structure is by imposing a bottleneck layer in the network. And this bottleneck layer actually forces a compressed knowledge representation of the input, and that is what the autoencoder learns, and this compressed domain knowledge representation is subsequently used for other applications. So, while doing this, we assume something. The assumption is the degree of correlation or the structure that exists in the input data is quite high. And in fact, if the input data or the input feature vectors are uncorrelated or they are statistically independent, then compression and subsequent reconstruction would be difficult. Of course, we will be able to compress, but the compression will be highly lossy compression if there is no redundancy, because whatever information is present in the input data, unless there is redundancy or there is correlation, then going for any sort of compression leads to loss of data. And once in that compressed domain representation, the data or the information is lost, whichever way I try to reconstruct my signal, the original signal, from that lossy compressed representation, my output will always be lossy. That means the decompressed data or deconstructed data cannot be identical to the input. So, the basic assumption in use of autoencoders, when you go for encoding in compressed domain or representation in compressed domain, the basic assumption is that data is highly correlated. So, based on this, we have seen a basic autoencoder architecture, which is something like this, that you have an input layer, you have an output layer. So, input layer actually accepts the input data. So, if the dimensionality of the input data is n, at the input layer I will have n number of nodes. In addition, there will be one more node to take care of the bias. And in fact, we have seen earlier that addition of this bias in the input vector allows us to go for an unified representation. That is, the bias term can be considered as an additional term in the weight vector. So, number of nodes in the input layer will be n plus 1 if the input data vector has dimensionality n. Similarly, in the output layer, which reconstructs the input as x hat. So, our input is x and the output is x hat. So, the output layer will consist of n number of nodes, because we want that the input x should be reconstructed at the output. And in case of a basic model of an autoencoder, we have a hidden layer in between input layer and output layer. And what we have said in case of undercomplete autoencoder, that the number of nodes in the hidden layer is less than the number of nodes in the input layer or the number of nodes in the output layer. So, this is what is known as a bottleneck layer. So, in bottleneck layer, as the number of nodes is less than the input layer nodes, so what this network does is the network passes the input information through a restricted layer where the number of nodes is much less. And then subsequently, as this information passes through this restricted layer, then the decoder side, that is the output layer, tries to reconstruct the original input from this restricted output. So, as the information passes through this restricted layer, the network tries to learn a compressed domain representation of the data. So, you imagine what will happen if I do not have this bottleneck layer. That is, if the number of nodes in the hidden layer is same as the number of nodes in the input layer, that is the size of the data, or even more than the number of nodes in the input layer. In that case, it might be possible that the network will simply learn an identity function, that is, given an input, it goes through an intermediate representation and then knows how to reconstruct the same output. And in the process, if I have large number of nodes in the hidden layer, the network eventually may not learn the compressed domain representation or the structure present in the data, which is not our aim. So, that is the reason that in the hidden layer or in the bottleneck layer, you put some restriction on the number of nodes that you can have. Later on, we will see that when we talk about the sparse autoencoder, that it is not even necessary to have the restriction on the number of nodes, but we can add some other regularization term where the red node activations will be restricted. So, instead of trying to restrict the number of nodes, you try to restrict the node activations. So, this is the basic structure of an autoencoder, and as we said that all subsequent representations we will use this form of representation diagram to represent an autoencoder. So, I have an encoder part which is the from input layer to the hidden layer, and I have a decoder part which is from the decoder to the output layer, and this whole thing taken together, the encoder decoder together, is known as autoencoder. And as it is an undercomplete autoencoder that we are trying to depict, the number of nodes in the hidden layer, which is the bottleneck layer, is less than the number of nodes in the input layer or the number of nodes in the output layer. And while training this autoencoder, the loss function that you try to minimize is the squared error loss between the input and output. So, that is x minus x hat L2 norm of that x minus x hat square, take the summation over all the data points, all the training samples that you are feeding for training this network. So, this is the basic structure of an autoencoder which has got one input layer, one output layer with a hidden layer or a bottleneck layer in between. Now, when you go for, so what does this autoencoder try to learn? So, here what has been shown is that if I feed an input to an autoencoder which is an image. So, in our case x is an image and the output, that is x hat, which is reconstructed, is also an image, right. And in ideal case, if the autoencoder is properly trained, then x hat will be same as x. Now, once this autoencoder is properly trained, what does this encoding layer or the bottleneck layer actually learn? So, this is an example which has been obtained from training such an autoencoder with large number of input images. So, you find that on the right hand side, the example image set that we have. So, this particular image, this particular sub image is actually the image or the structure which is learned by the first autoencoder. Now, here you find that this output is not exactly from this particular network that we are showing here. Here you find that there are 100 such sub images or 100 structures. That means the autoencoder which has been trained with for this kind of example has 100 number of nodes in the middle layer or in the bottleneck layer, and every node learns some structure. So, this first node learns this structure. Similarly, second node may learn this structure and so on. And how this image has been formed? It is nothing but these weights from the input which are connected to the first node. You remember the way we have got this vector is by concatenating the columns of the input image. So, when you form these structures, when I reconstruct these structures which are learned by these hidden layer nodes, these are these weight vectors which are folded back in the form of an image. Okay. So, you find that if there are n number of nodes in the input, so I have an image consisting of n number of pixels. Here also I have n number of vectors, of course, n plus 1 considering the bias term. Now, when you form this, you remove that bias term. So, among the remaining vectors, remaining components of the weight vector, I fold it back in the form of an image. So, this is such an image. So, these are the structures as shown in this set of images which are learned by this encoding layer. And as you see over here, these sub images appear to be edges oriented in various directions. So, edges are nothing but the detailed informations which are present in the image. So, this simple example shows that these input layers or nodes in the input layer actually learn the structures which are present in the image. It does not simply pass the input image to the output layer. And then what this decoder side does is, the decoder side makes use of these structures which are present in the image, and from these structures it tries to reconstruct the original image. So, when this network is properly learned, this is the form of structure which is actually learned by this encoding layer. Right. So, this is how an encoder learns the structure which is present in the data. In case of deep autoencoder, so earlier what we have shown is a basic structure of an autoencoder where I have an input layer, I have an output layer, and I have one hidden layer which is a bottleneck layer. In a deep autoencoder, I can have a number of such autoencoding layers which are stacked one after another. So, in this diagram what has been shown is, this is your input layer, this is the input layer, this is the autoencoder layer 1. So, I put it as AE1, this is AE2, or this is actually the coding layer in this particular diagram. I can have AE1, AE2, AE3, AE4 and so on. I can go on stacking such autoencoder layers. Okay. Then accordingly, on the decoder side also I will have stacking of a number of such decoding layers. Okay. So, in case of deep autoencoder, the number of layers, number of encoding layers and the number of decoding layers that you make part of the autoencoder, that decides what is the depth of the autoencoder that you are going to design or the autoencoder that you are going to use. However, for training the autoencoder, we still use the squared error loss between the input and the output for training the autoencoder. So, given this, here you find that what this autoencoder does, as we have already said, that given an input data of dimension say n, so x having dimension n, if in the encoding layer or in the bottleneck layer I have the number of nodes which is equal to d, where d is much less than n. So, here this autoencoder learns a compressed representation of this n-dimensional data to a d-dimensional representation, which is the latent, also called as latent space representation. And it is expected that if the autoencoder is properly trained, then from this latent space representation, the decoder will be able to decode this latent space representation of the data to give you the reconstructed data exact, which is almost a replica of your input data X. So, in other sense, we can say that while coding, the autoencoder actually gives you a transformation that transforms the data from a higher dimensional space to a lower dimensional space. And while doing so, it ensures that your reconstruction error, end-to-end reconstruction error when the data will be reconstructed, that is minimized. So, this lower dimensional representation indicates that the loss, it tells that the loss that you incur while compressing the data or while trying to extract the structure from the data, the loss incurred will be minimum. So, in other case, you can consider the function of the autoencoder is to go for dimensionality reduction of the input data. And if I consider the function of the autoencoder as a dimensionality reduction function, then we have to see that what is the other dimensionality reduction function that we have. And it is known that traditionally the dimensionality reduction is done by an algorithm known as principal component analysis. So, naturally then the question comes that how does principal component analysis compare with autoencoders? So, in order to do that, before going to that comparison, for the benefit of those who does not know what is principal component analysis, let me briefly say what is principal component analysis. So, in case of principal component analysis, our input is, let us assume that input is a set of vectors x. So, I put this as set of vectors x1, x2, x3 up to say x. Xn. So, assuming that we have n number of input vectors, and each of the input vector may be of dimension, say, let me put as capital D. So, capital D is the dimension of the input vectors. That means, each of x1, x2 up to xn, each of them has d number of components. Now, once I have such a collection of vectors x, you define the covariance matrix Cx, which is defined as expectation value of x minus mu x into x minus mu x transpose. What is mu x? Mu x is nothing but mean of the input vectors. So, I have n number of input vectors. So, this will be 1 upon n sum of x I, where I varies from 1 to n. So, this is my mu x, and x is each of these individual vectors. So, I define the covariance matrix of the set of input vectors as the expectation value of x minus mu x into x minus mu x transpose. And now, if you analyze this covariance matrix, so what will be the size of this covariance matrix? As the vector is n dimensional, so this covariance matrix will be a d by d matrix, as d is the dimension of the feature vectors. So, this covariance matrix will be a d by d matrix, and in this covariance matrix, the diagonal elements will give you the variance of the individual components of the vectors. That means, if I take the first vector, first component of x1, first component of x2, first component of x3 and so on, and I compute the variance of all those first components, that variance will be my sigma 1 1, which is a first component in this diagonal vector. Similarly, sigma 2 2 will be the variance of the second component, sigma d d will be the variance of the dth component of the last component. And all the off diagonal elements in this matrix will give you the covariance of different components. So, sigma 1 2 is the covariance between the first component and the second component. Sigma 4 5 is the covariance between the fourth component and fifth component, and so on. So, this is what is your covariance matrix. So, once I have this covariance matrix, then from the covariance matrix I can compute the eigenvalues and the eigenvectors. So, suppose how do you compute the eigenvalues and the eigenvectors? Given a covariance matrix Cx having say sigma 1 1, sigma 1 2 up to sigma 1 d, sigma 2 1, sigma 2 2 up to sigma 2 d, and so on. This is sigma d 1, sigma d 2 up to sigma d d. So, this is say my covariance matrix, and I want to compute the eigenvectors I and the eigenvalues lambda. So, the way you compute this eigenvalue is from each of these diagonal elements you subtract lambda and then make a determinant. So, the determinant will be sigma 1 1 minus lambda, sigma 1 2 up to sigma 1 d, sigma 2 1, sigma 2 2 minus lambda, sigma 2 3 goes on, sigma d 1, sigma d 2, sigma d d minus lambda, make a determinant and equate this to 0. So, once you put this, you find that this determinant will give you a polynomial of degree d, and it will be a polynomial in lambda. So, once I solve this, I will get d components or d values of lambda. So, I will get lambda I, where I varies from 1 to d. And then for each of this lambda I can compute the corresponding eigenvector. So, the way you compute eigenvector is, if for lambda I the corresponding eigenvector is say E I, then the equation that has to be satisfied is C x E I have to be equal to lambda I times E I. So, I know what is C x, I know what is lambda I. You solve this equation, I get the ith eigenvector, which is E. So, this is how, given a set of vectors, I can compute the covariance matrix. From the covariance matrix, I can compute the eigenvectors or eigenvalues, and for every eigenvalue, I can compute the corresponding eigenvector. And you see that if this covariance matrix is real and symmetric, which usually is, then the eigenvectors are orthogonal. And what this lambda tells you, or the eigenvalue tells you, it simply tells you that what is the scatter or what is the variation of the data in the direction of the corresponding eigenvector. So, if lambda 1 is very high, that indicates that the variation of data in the direction of the corresponding eigenvector, which is E1. So, lambda 1 very high indicates that the variation of data in the direction of E1 is very high, right. So, given this, once I have this eigenvectors, then I can define a transformation. So, how do you define this transformation? For defining a transformation, you form a transformation matrix A. This transformation matrix A is formed using the eigenvectors as the rows in the transformation matrix. So, the first row in this transformation matrix is E1, the second row is E2, the last row is ED. You remember that we had D number of eigenvectors as our input vector is of dimension D. And how I get this transformation matrix, or how I arrange such eigenvectors into rows of this transformation matrix is, in this transformation matrix, E1 corresponding to that my eigenvector is lambda 1, and for vector E2 my corresponding eigenvalue is lambda 1, and corresponding to this I have my eigenvalue which is lambda 2. So, I arrange these eigenvectors as rows in this transformation matrix in descending order of the corresponding eigenvalues. So, here E1 is the first row, E2 is the second row, that indicates that I have lambda 1 greater than lambda 2, right. So, for a pair of eigenvalues, say lambda I, lambda j, where both I and j varies from 1 to d, because I will have lambda varies from lambda 1 to lambda d. So, for this pair of eigenvalues lambda I and lambda j, if lambda I is greater than lambda j, that indicates that EI, the eigenvector EI, will occupy a higher row than EJ in this transformation matrix. So, for this EI, I have the corresponding eigenvalue lambda I, for EJ I have the corresponding value lambda j. So, as lambda I is greater than lambda j, in this transformation matrix A, EI will occupy a higher position than EJ. So, that is how this transformation matrix is formed. So, once I have this transformation matrix, then I can define a transformation. My input vectors are x. I can have a transformation which is given by A times, say, x k, the kth vector, minus mu j, mu x, which is the mean of the vectors. So, this defines a transformation. So, this gives me a transformed vector which is y k. So, for kth vector, this transformation gives me a transformed vector y k. So, if you look at this transformation, what this transformation is doing? If I take the first component of a x k, so difference of first component of x k and first component of mu x, right, this is transformed, or the vector x k minus mu k is being projected onto vector E1, because this is nothing but the dot product of E1 with x k minus mu x, that gives me the first component of y k. Similarly, the dot product of x k minus mu x with E2, which is the second row in my transformation matrix, gives me the second component of y k, right. So, this transformation that you get, this is what is popularly known as KL transformation. And I can use this KL transformation for data reduction in the sense that if I want to reduce the dimension from D to 2, what I will do is, in this transformation matrix A that I form, this A, instead of considering all the eigenvectors, I will only consider E1 and E2, the eigenvectors E1 and E2. And the transformation will be same as this, A times x k minus mu x, where A is now, this is actually 2 by D matrix. I have 2 rows and D number of columns, right. So, this is a 2 by D matrix. So, when you go for this transformation, this y k, you find that it will be a 2 by 1 vector, that means it is a 2-dimensional vector. So, just by truncation of this transformation matrix, I can transform the data from n dimension to 2 dimension, or d dimension to 2 dimension. So, that is what gives me a reduction in the dimensionality of the input data. And this is what is popularly known as KL transformation, and the components of this transform vector yk that you get, that is yk1 the first component and yk2 that is the second component after this transformation, these are what are known as principal components, and the eigenvectors are the principal directions. So, effectively what you are doing is you are transforming your input data into a space which is known as eigenspace, and the eigenvectors being orthogonal, the eigenspace is also orthogonal, and the projections in the eigenspace in every eigendirection are the principal components of the input data. And by arranging the transformation matrix A in this form, that is arranging the rows as eigenvectors in descending order of corresponding eigenvalues, ensures that the error that you encounter by truncating some of the rows from the lower side ensures that the error that you encounter will be minimum. So, let me stop here today. I will take up this illustrations with principal component in the next class. Thank you.